This is the second podcast in the part of Programming Paradigms about type functional programming in Haskell. In this podcast, we'll be covering mostly lists and we'll introduce user-defined data types. And there's a lot you can do with recursive data types. First, let's have a look at the learning goals.
So what are the learning goals for this particular session? The first learning goal is that you must understand lazy evaluation and how it works. Another important learning goal is that you should be able to write programs in Haskell that use lazy evaluation. Concerning lists, an important goal here is that you must be able to understand and be able to use common functions on lists in Haskell and to understand their types. And this includes the functions map, filter, fold left and fold right. As for recursive data types, the learning goal is that you should understand and be able to use recursive data types in Haskell to express structured data. And that you can define recursive functions over recursive data types. And finally, that you can understand and use list comprehension and ranges. So this session is all about lists, functions on lists, and recursive data types and functions on recursive data types. These are some of the most interesting features, not all of them, but some of the most interesting features in Haskell. First, let's look at lazy evaluation. We've already seen lazy evaluation in the setting of Haskell. We know that Scheme has the force and delay primitives, but Haskell always uses lazy evaluation by default. This means that in a function application f of some e is evaluated at most once. That is only if we need it. So that's the lazy strategy. We could also imagine an eager strategy, which is called by value. Namely that whenever we have a function application f of e, the argument e is always evaluated, even if we do not need it. Now Haskell, as I've just said, uses lazy evaluation, whereas the languages of the ML family, SML, OCaml, and F# use eager evaluation. And that's one of the major differences between these two otherwise fairly similar languages. Now it's fairly straightforward to define how you actually carry out lazy evaluation. The semantics of lazy evaluation is quite simple. In fact, there's one reduction rule that we know from before. That's a beta reduction rule, saying that if we have an abstraction lambda x e1 and we apply that to e2, this reduces to e1 where all occurrences of x have been replaced by e2. This is substitution. But to define lazy evaluation, we need a further rule for application, namely one that says whenever we have an application e1, e2, then this can only reduce if e1 can reduce to some e1 prime, and then the whole application reduces to e1 prime, e2. So taken together, these rules will ensure that we never evaluate the argument of a functional application. We never evaluate the actual parameter. All we do, whenever e1 is an abstraction, all we do is we then substitute e2 into the body of the function. lambda x e1. You may recall that what we have here is actually what's known as normal order reduction. To see that we can get more out of lazy evaluation than we could with eager evaluation, here's a small example. Consider the program that defines the function blah. Blah of x is defined to be blah of x. And we defined another interesting function h. H of z is always 7. Let's send this to the Haskell interpreter. Everything works out fine. Now you may ask, what's the value of applying h to the argument blah of 8? Well, it's 7. Why is that? Well, because here in h blah of 8, we never evaluate blah of h before we substitute blah of 8 into the body of h. So we substitute blah of 8 into 7. Nothing happens. We get 7. Now, one could imagine having applicative order instead of lazy evaluation. One could have call by value, as it were. And if we want that, we can use the extension bang patterns. We can write set x bang patterns. Yep. And then we redefine h to be a function with a call by value parameter, h bang set. And now let's call h of blah of 8. See what happens. H blah of 8. And lo and behold, this leads to nothing, because we're trying to evaluate blah of 8, and blah of 8 is defined to be blah of 8. So the evaluation of the actual parameter does not terminate. So this will not give us a result. So call by value is indeed not as powerful as lazy evaluation, as this example shows. Now let's discover how we can use lazy evaluation to define infinite structures, because that's possible in Haskell, and this is really quite surprising perhaps, but it's very useful. Remember that the list notation is really just a shorthand. When we write, say, 1, 2, 3, 4, 5, that's really just a shorthand for saying, let's take the empty list and then cons 5 onto that, and then we'll cons 4 onto that, and we'll cons 3 onto that, and we'll cons 2 onto that, and we'll cons 1 onto that. So a list is just a repeated application of cons to the empty list. And we can use that to define infinite lists. For instance, we could define the list of ones, the infinite list of ones, as ones being equal to 1 const onto ones. Using the terminology from Scheme, what we have defined here is actually a stream of ones. And this is meaningful whenever we only want to retrieve a finite part of this infinite structure. Let's see how that's done. To do this, we'll be using the take function that's found in the Haskell prelude. And take is a function that is a function from int to a list and returns a list of a elements, and it should satisfy that if we apply take to n of l, then this gives us the list of the first n elements of the list L. Now you might ask, what is take 5 applied to the list ones that we just defined? Let's see what Haskell has to say about this.
have the list ones, which is the infinite list of ones. So it's one const with ones. What happens if we take the first 5 elements of ones using the take function? We get a list of 5 ones, which is good. But then you might wonder, what happens if we try to evaluate ones? What do we get then? We should get an infinite list. And lo and behold, that's indeed what we get.